Have you ever seen one of those videos of a factory robot assembling a car with like perfect precision, or a robot dog that can run and jump over obstacles? Well, you've seen the magic of kinematics in action. Today, we're going to pull back the curtain and look at the hidden geometry that makes all of that possible.
So, let's start with the big question, right? Whether it's a huge industrial arm or one of those eerily human-like robots, how does it know exactly where to put its hand or foot? That is the fundamental puzzle we're going to solve together today.
And you know, the answer is actually surprisingly close to home. Just think for a second about reaching out to grab a glass of water. You don't calculate the physics or the forces, do you? No, you think about the goal and your arm moves. For robots, it's the same basic idea. It all starts with the geometry of motion, just like our own bodies.
And that idea, focusing purely on the geometry, that's really our first big piece of the puzzle. It's all about understanding the positions and angles that dictate every single move a robot is going to make.
The science behind all this is called kinematics. And here's the key thing to get. Kinematics is not about the forces. It's not about the motors, the electricity, or what's actually powering the robot. Nope, it is purely about the geometry, the positions, the angles, the path. It's the how of the movement, not the why. So when engineers are figuring out this how, they're actually solving a two-part puzzle. You can think of it as two sides of the same coin, the forward problem and the inverse problem.
Okay, this slide breaks it down perfectly. On the left, you've got forward kinematics. Honestly, this is the easy part. It's like, okay, if I set all my robot's joints to these specific angles, where does the hand end up? It's a straightforward calculation. But the real magic, the much, much harder problem, is over on the right. Inverse kinematics.
Inverse kinematics flips the whole script. It starts with the goal. It says, I need the robot's hand to be right here. Then it has to work backward and figure out the exact angle for every single joint to make that happen. This is incredibly complex because often there's more than one way to reach the same spot. The real challenge is finding the best, most efficient path, and solving that is what makes a robot so useful.
But you know what? Just getting to the right spot isn't the whole story. For a robot's movement to be truly effective and, well, not a clunky mess, we have to think beyond just the final position.
This table lays it out so clearly. Position, that first row, that's what we've been talking about, getting the parts to the right place. But look at the second row, velocity. If a robot is painting a car door, the speed has to be perfectly consistent, right? Otherwise, you get a blotchy paint job. And finally, acceleration. You can't have a giant, heavy industrial arm just jerking from 0 to full speed. Controlling its acceleration is what makes the movement smooth, safe, and efficient.
So how on earth do engineers actually calculate and control all of this? Well, it is definitely not guesswork. They rely on a really powerful and precise mathematical toolkit to get the job done.
Think of this stuff as the literal language of robotic movement. Engineers create a virtual map of the robot, using coordinate systems for every single joint. Then they use these mathematical tools called matrices to calculate all the rotations and translations, basically how all the different parts move in relation to each other. It's a systematic way to describe the robot's entire geometry so that these incredibly complex movement calculations can be solved reliably every single time.
Okay, so that's the theory. But this isn't just some abstract math problem. The impact of kinematics is all around us, in some pretty amazing ways. Seriously, the applications are incredible. We see it on the assembly line, where robotic arms are welding cars together. It's in the operating room, guiding surgical robots to perform incredibly delicate procedures. It's the secret sauce that lets humanoid robots walk and stay balanced. And yep, it's even at the very core of how self-driving cars figure out how to navigate the world. So the first huge benefit here is precision. Kinematics is what allows a robot to pick up a tiny microchip without crushing it, or what allows a surgeon to control a tool inside the human body with sub-millimeter accuracy. We're talking about a level of precision that is, frankly, superhuman.
The second benefit, and this is the one that's maybe a little more awe-inspiring, is creating lifelike movement. For a humanoid robot to just walk across a room, or balance, or grab something without falling flat on its face, it has to constantly be solving that super complex inverse kinematics puzzle for its entire body. It's amazing.
I think this quote really just sums it all up perfectly. At the end of the day, kinematics is a cornerstone of modern robotics. It's the bridge between abstract geometry and physical motion. It's the translator that lets machines interact seamlessly with our world.
So here's the big takeaway, right? By mastering the geometry of motion,
We've given machines this fundamental building block of, well, of a kind of intelligence. They can now navigate and interact with the physical world with incredible grace and precision. Which leaves us with a final, really fascinating question to think about. Now that robots are mastering movement, what's the next big barrier they're going to cross? Thanks for joining me.